Resume recording. Good. So let's just review quickly, right? And so you can put it, so you can record it in the. So today is May 1st. We are continuing electromagnetic waves. Very quickly, just revising what I mentioned before. Okay, those exams, the exam is currently scheduled for May 17th. It may be possible for us to change the date of this exam if you need more time. And we cover chapter 22, okay, which is the law of induction. We cover, those are the chapters, those are the sections we cover, which cover chapter 23 on AC circuits, and now we are covering electromagnetic waves. I'm expecting to cover section 1, 2, 3, 4, skip 5, and cover 6. And now what am I doing? I am explaining to you how electromagnetic waves comes about from the equations, from electromagnetic equations. And I'm going to copy and paste all those laws of electricity and magnetism. Okay, what predicts the existence of electromagnetic wave is those two equations. Okay, that's what predicts. Those two equations alone, even though you have 5, right? But it is those two equations alone that predict the existence of electromagnetic waves. Okay. Here you go, Faraday's law of induction. I'm gonna put that first. And then we have this other law, right? I initially introduced you this term here for this law, but then later on, someone called James Clerk Maxwell discovered that there was a missing term in there. And now notice that both, and I gotta put also I gotta put also this thing here. Should be a summation, okay? And induced. So you already know that a changing magnetic flux induces an electric field. Okay, initially we didn't have this term here, and you know that it is a current that's the source of a magnetic field, but then later on, James Clerk Maxwell discovered something else, discovered that this equation required a second term. Notice that here I have a magnetic flux, and here I have an electric flux. So when people look at that and said, look, a changing magnetic flux induces an electric field, you know, they saw symmetry in those equations. They saw that a changing electric flux also induces a magnetic field, okay? So this one here is the regular magnetic field that's induced, that the magnetostatic, right? And this one is the regular magnetostatic field. I didn't put induced there. Notice that I didn't put induced there. And this term here is the one that induces the magnetic field. And now we have this symmetry in those equations in which both a changing magnetic flux and a changing electric flux induces their counterpart magnetic fields and electric fields respectively. And that's what gives rise to electromagnetic wave. That's what gives rise to electromagnetic wave. Okay, and then I'm walking you through a qualitative way of applying those equations. Okay, I want you to practice that at home. Okay, right-hand rule and all that stuff. So again, we're going to start with a magnetic dipole, which is a loop of a current. Now, I don't show here that there is an AC. What I don't show here is that this guy is connected to an AC source, okay? And I didn't illustrate the AC source, but this guy is connected to an AC source. At a given instant of time, the current is increasing, and it is in the clockwise direction. Because of the clockwise direction of the current, there is a magnetic field generated by this current loop. Okay? There is a magnetic field generated by this current loop, which is exactly this term right in here. From this term alone, we already know that there is a magnetic field, which, by the way, decreases as you move further and further away from the source. Okay, B field generated by the current loop, by the current loop. Okay, field generated by the current loop is also a function of time because the current is changing as well. Let us say that this function of time at this given instant of time, the B field is increasing, just for the sake of the drawing here that we have. Okay, see. Oh, okay, so I'm gonna put this way. I gotta switch those two slides. Okay, B field generated by the current loop, B field decreases as it goes further away from the source in that small portion of space. Okay, and B field generated by current loop is a function of time. And let's say at a given instant of time, this B field is increasing. Since the B field is increasing, this B field will induces an electric current that is going to counter the direction of the B field. You can see that each magnetic field line is inducing an electric field in the counterclockwise direction, okay? That's what those guys are all about. They are an arrow indicating the direction of the electric field. If we had a conductor right here, oriented in the proper direction. Suppose that we had a conductor right in here, right? Oriented in the proper direction. Then eventually I'm going to, at this very instant of time, the electric field here is going to power a current in this conductor. Okay? Suppose that, right? Now, the same thing cannot be said about this conductor being here. So let's say this conductor being here. Okay? Why is that? Because the B field here would be in this horizontal direction, horizontal section here of this wire, and the current wouldn't be able to move along the conductor. Can you picture that? Okay. So the only way that this field would induce a current in this conductor would be here at the edges of this circle. Okay, but notice something else too. This electric field here, due to this magnetic field line, has a direction contrary to this other electric field here at the top, due to this magnetic field line. Okay? And what can you conclude from that? We can conclude from that we are going to have only electric field lines in the vertical direction. Okay? This cancel out, this one cancel out this one. Consequently, on the left side, there will be a electric field upwards. On the other side of this magnetic field, there will be another electric field pointing downwards. And what about for this one? These magnetic field lines will induce an electric field upwards. This is exactly what you're seeing here. Downwards, upwards, downwards, upwards, downwards, right? And you have a bunch of magnetic field lines that's going to behave like that. One more important detail. Because this magnetic field here is stronger than this other magnetic field, it will also induce an electric field that's stronger than this other induced electric field. And I illustrated that by putting the by putting the arrows longer and shorter, right? Induced electric field is stronger than this one, but wait a minute, because this guy here is generating this electric field on this side, this other electric field is going to have the same magnitude as this one, but because it's on the other side of the line, then it should be downwards, right? Because this magnetic field here is lower than the other one, it will also induces a weaker electric field. And by the way, on the other side, you're going to also have an induced electric field that's going to have the same intensity, but opposite direction. Okay? Because those two magnetic field lines are very close to each other, one is going to cancel the other. This is going to cancel this one, this is going to cancel this one, and so on. So at this very instant of time, the resulting electric field in between those magnetic field lines is going to point downwards. Okay? That's the idea that you must have. And that's for the case of the magnetic dipole. If you repeat that for the electric dipole, it's going to be the same thing. Okay? So now you have those electric and magnetic field lines in space. Okay? And notice that they are perpendicular to each other. Notice that they are perpendicular to each other. They make an angle of 90 degrees. What else do we have to know? What else do we have to know? Okay, if we invert at another instant of time in which the current is on the other direction, the fields become inverted. Okay, the fields become inverted. If the magnitude of the magnetic field is increasing, then the direction of the induced electric field is going to be upwards. Going back to that other drawing. Now, what else do you have to know? Okay, that's something that I cannot prove here for you because it requires calculus, okay? What we learn as well is that from the equations is that those lines of electric and magnetic field, they behave just like a wave, okay? A wave that propagates from the source. So at a given instant of time, those magnetic and electric field lines are going to be here. A little bit later, they're going to be here, and so on, okay? Here, I didn't put the wavy nature of this electric and magnetic field. They tag along, the electric and magnetic field tag along with each other, okay? And I'm going to show you, I have already shown that to you before. I'm going to show that to you again. There is a simulation of those electric field lines. Is that here? No, it's not here. Gotta go back into YouTube. Okay, well, let's go into YouTube. Electromagnetic waves simulation. Let's see. Let's take a look at this one. Let's see if it's a good one. Oh, physics, huh? Let's see. Yeah, okay. So let's see. Gotta get this thing moving. Must be playing here, right? Yeah, it's going too fast. I don't like it. It's going too fast. Let's see if I can slow it down. See, that's the direction of electromagnetic wave from the left to the right. What does it mean? It means that my electromagnetic source is to the left. If it doesn't show it, it can be either, let's see, the green is, which one is the which, right? Show plane of wave corresponding, show plane of electric field. Okay, the electric field is in the vertical direction. Okay? Show electric field component. It's going to be the green. The green one is the electric field. Okay? So if the antenna is an electric dipole antenna, what we end up having is is an antenna that is going to be, is a loop that's going to be in the vertical direction, the direction of the electric field component, the plane, right? The plane of the electric field. Can you picture that? It's going to be on the green plane. If this is a electric dipole antenna, the antenna is going to be in the vertical direction here. Again, in the direction of the electric field, of the plane of the electric field. Okay? That's one simulation of that's how you should picture radio waves, electromagnetic fields. And we also have some you know, I like this video, okay, showing in real life how we end up getting an electric theory. Let's see. I'm going to skip the theory, okay? So the story goes like that. Maxwell discovered the correction to one of the laws of physics of electricity and magnetism, and but he just Maxwell was just a theoretical guy. Later on, someone called, a university professor called Hertz, William Hertz, demonstrated experimentally the existence of electromagnetic waves. And here there is this guy with this video that shows more or less how Hertz experiment went about, okay? Today we can do this experiment rather easily because we can buy stuff off the shelf. But back in the 1850s and 1860s, 1870s, we couldn't get those things easily. Okay, they were just experimental devices. Nowadays, you know, they're all mass manufactured. It's so easy to purchase one of those, you know. So he got.
Around 1880, the brilliant scientist James Clerk Maxwell developed the mathematical theory of electromagnetism. His theory predicts that electromagnetic waves propagate through space at the speed of light.
Okay, you go. Electric field, magnetic field, they're perpendicular to each other.
Many other scientists of the time.
And remember, you know, the distance between every other node is the wavelengths of the wave, right? Just like we covered in physics 37, in physics 6.
We're trying to prove experimentally the existence of this wave. In 1887, Heinrich Hertz, a German physicist, designed a series of brilliant experiments to demonstrate Maxwell's hypothesis.
That's how, you know, cell phone communications started. That's how wireless communication started, with those two guys, okay? And then there was a third guy, very important guy, that's called Guglielmo Marconi. He won the Nobel Prize because he was the first one to put to practice in an industrial scale the experiment that Hertz himself performed.
Heinrich's equipment was simple: a spark generator coupled to an antenna.
Okay, see here we have this is the antenna, right? And this is an electric dipole antenna. This is an electric dipole antenna. And what he did, he had a solenoid here to generate a buildup of charges in those two spheres. Okay, and the amount of charge here varies as time goes by, okay?
And a metallic ring set at some distance apart. Heinrich.
Okay, here is the transmitter, right? And what is this one here? Here's the transmitting antenna, and this one is the receiving antenna. This device here is not much different from this device here. The only difference is that this is an electric dipole antenna and this is a magnetic dipole antenna. Okay? And it must be oriented in a proper direction. So it will receive the waves, will collect the waves that's being transmitted from this guy.
Which proposed that the electromagnetic waves generated at the antenna will travel through space, and if Maxwell's theory was correct, they would induce a current in the ring, and a spark will appear in the ring gap. In this video, we make a simplified version of this famous experiment.
Okay, and I'm gonna copy this one here and put in my notes. Okay, for a video on electromagnetic waves. For a video on the generation and detection for a video about for a real life video about the generation and detection of electromagnetic waves. See, no, I missed my, go here. See, yep, this video here. Okay, so what this guy have done, he produced this experiment with 21st century materials. 8 years ago, yeah, it's 21st century materials that you can buy off the shelf. Okay.
This project requires a high voltage pulse in order to work, and we will obtain that pulse with a lighter like this.
Okay, do you recognize the stuff here? You know, Hertz didn't have something like that at the time, but it does exactly what that other device, the transmitter, does. Okay, so
here we have one that we have modified.
Oh, he modified that. Okay, he took out the tip, but he put those two wires here.
Let's open the lighter. Here it is. This is a piezoelectric element that produces a pulse of several thousand volts. There are these two wires that come from the piezoelectric, and we have connected these two wires in order to be able to get the pulse. Here we can see the spark.
The electric dipole antenna. See the sparks? It's an electric dipole antenna. You see the sparks because the charge that's building up here is large enough to ionize the air around those two tips. Okay, one tip of the wire becomes positively charged, the other becomes negatively charged. If you build enough electric charges here, they will have nowhere to go but to discharge through the air, and they discharge through the air by ionizing the air and goes from the one to the other. Hertz did something similar. It's those two spheres that you saw. What you had, those two tips here represent those two spheres that you saw in the initial drawing.
Okay. Pull the trigger.
So we are having a change in electric charges here. The electric charges are changing at this very tip as time goes by, and is generating an electric field that changes in time. This electric field that changes in time is inducing a magnetic field that changes in time as well. Okay? And how was Hertz's experiment? Here you go. Here's the transmitting antenna. Okay, see the spark generator right in here, and the tips, the two tips, the electric dipole. One is going to become positively charged, the other is going to become negatively charged, and this charge is going to change as time goes by. When this charge changes as time goes by, you know, this charge has an electric field. Because the amount of charge that's changing as time goes by, it generates an electric field that changes in time. And this electric field that changes in time also induces a magnetic field that changes in time. How do you see if the electromagnetic wave propagates from here to here? Okay, we see that according to the law of induction. Because the electric field is changing here, this wave is going to propagate to the other side and is going to induce a current in this receiving antenna. And what you're going to end up here seeing is that you're going to see that this source is going to light up. Okay, this source needs not to be connected to the power source, to the wall, to light up. All you need is an electromagnetic field that's strong enough to power it up.
This is our setup to replicate Hertz's experiment. We have the spark generator.
In Hertz's experiment, by the way, he didn't have a light bulb. Okay, instead he had that ring, right? with the spheres at the tip of the ring, right? Remember that? And then, so how did he manage to prove to his colleagues that electromagnetic field waves propagate from here to here? Okay, so the way he proved was by observing a spark that was being generated here at this tip. This guy was not connected to any power source whatsoever. This one is connected to the power source. So if there's any spark here, it's because of the power source. But if we observe a spark here on the other side and this circuit is not connected to any power source whatsoever, the only explanation for the existence of the spark or the light up of this bulb is going to be the existence of the electromagnetic wave that's going from one transmitting antenna to the receiving antenna. Okay? There you go.
To these two wires, and the electromagnetic waves will travel through the receiving antenna. Here we have a neon lamp connected to the antenna, and when the spark is produced here, the neon lamp will glow.
Okay, so here you go.
Okay, I will pull the trigger to generate the spark.
Okay, do you see the light
now we can
flashing briefly here?
Glowing.
This is electromagnetic induction. We don't see the spark here, but we do see the light bulb momentarily turning on and off. Oh, now we see the spark, right? Okay. I don't see the spark now, but I see the light bulb flashing.
We will now try a more powerful arrangement.
Okay, that's now when you get into trouble, right? Instead of this little device that provides a very low current here, he's gonna come up with something far more powerful. And that's what he said.
We are using now high voltage power supply. You can build this power supply following the link to the video that is now on the screen. This power supply outputs several thousand volts. The output of the power supply is connected to this capacitor. The capacitor stores the energy, and the spark will be more powerful in our transmitting antenna.
Okay. Watch it. Look at here's the spark, and here's the light bulb flashing. There you go. So that's experimental demonstration of the existence of electromagnetic waves. Okay, we're gonna move away, and the electromagnetic wave is gonna become a little bit smaller here. As a result, the light bulb is gonna flash a little bit quicker. Okay, so I like this video. Okay, so let's I already mentioned that before, right? Let me see if I already wrote that down. See. Yeah. A changing magnetic flux, and you go the other way to a changing electric flux induce a magnetic field, right? So all this story that I mentioned to you is documented right here. Going back to our book. Yeah. Nature of electromagnetic wave. Here you go. Here's an electric dipole antenna, right? I mentioned that to you. That's exactly what he had there. Here now we have what could be regarded as a magnetic dipole antenna. All you have to do is to close it, close the circuit. And here is the electromagnetic wave generated by this electric dipole antenna. Electric field is parallel to the direction of the antenna. Magnetic field is perpendicular to the direction of the antenna. That's because the flow of current here is going to generate a magnetic field that circulates around the wire. Because this is the source of the current, the electromagnetic wave is going to propagate from the left to the right. Okay, and here is the other half of the circuit. Here is the receiving antenna. Okay, here's the receiving antenna. Notice that we have a gap here. You must have a gap between those two conductors, just like you had a gap there in the experiment. The electric field, the incoming electric field, powers up a current here in this wire. If too much charge accumulates right in here at those two ends of the rod, you're going to see a spark. Okay? This antenna is coupled to an LC circuit for a very good reason. Notice that we have an inductor and a capacitor. Okay, a capacitor, by the way, that I can tune the capacitor. There's a very good reason for that. Okay, I tune the capacitance so I can get the right frequency of the circuit that's going to match the frequency of the wave. That's what it is. That's what your tuning radio is all about. Okay, when you're turning the knobs in the radio, you are either changing the inductance or the capacitance of the wave to tune to electromagnetic wave that has a specific frequency. Okay? And, antenna is coupled to another circuit. It's an inductor, right? What basically that we have here is a kind of a transformer that goes to your audio video amplifier circuits to listen to your music or even watch your TV. It works both for TV stations and radio stations. Okay, well, that's wireless transmission. That's wireless transmission. So let's and note, see, here you go. We have this antenna is in the vertical direction, right? If you have instead a loop, right? An magnetic dipole antenna. Notice that this circuit is exactly the same as this other one. The only thing that's changed is the geometrical configuration here of the antenna. The antenna must be, the plane of the antenna must be perpendicular to the magnetic field. The direction of wave travel. Guess here, we are going to end up having a change in magnetic flux. A change in magnetic flux induces an electric field that powers a current in the circuit. And now we have a circuit carrying current without a power source, but just a changing electric and magnetic field. Okay, so let's, I want to, even if you have to repeat what I did before, right? So here you go. How to generate electromagnetic wave. How to generate an electromagnetic wave. Okay. You can use either an electric dipole antenna, or magnetic dipole antenna. Okay, that's your transmitter. Okay, one. In the case, let's see, in the case of an electric dipole antenna, A. We have an accumulation of electric charges at the tip of the antenna. One tip is positively charged, and the other tip is negatively charged. Okay, B. You don't have to have that spark to generate an electromagnetic wave, okay? Okay, the amount of charges at this tip. I'm referring the inner tip, right? Let's put the inner. Well, let's see, at the inner tip of the antenna, at the inner tips of the antenna. One inner tip is positively charged at a given instant of time. At a given instant of time, one tip becomes positively charged and the other negatively charged. The amount of charges at both tips, right? Both inner tips change as time goes by, okay? These tips, these charged tips, yeah, these charged tips generates an electric field that changes in time. Okay, these charged tips generate an electric field that changes in time. These fields, these E fields, this E field, these, right? E field that changes in time induces a magnetic field perpendicular to the E field. Okay. The B field tags along with the E field. Both, let's see, both E field and B field propagates away from the antenna at the speed of light, propagate, right? Discharge tips generate an electric field that changes in time. Their behavior, that of a wave. A wave. Okay. Now there's more. That's the transmitting part. Further away, it is possible to detect these waves with another antenna. Okay? We have an accumulation charge at the tips of the antenna. We mentioned one positive charge and the other negatively charged. This is, I'm gonna put that, this is the transmitting antenna. The amount of charges at both either tips of the transmitting antenna, right? Change as time goes by. As time goes by. Discharged tip generates an electric field that changes in time. This field changes that changes in time induces a magnetic field perpendicular to E field. Both the field and B field propagate away from the antenna at the speed of the light. The B field tags along with the E field. They're propagating They are propagating behavior that of a wave. Further away, it's possible to detect this wave with another antenna. Either an electric dipole antenna, or magnetic dipole, either an electric dipole or magnetic dipole antenna. Okay. In the case of an electric dipole antenna, it's preferable that the antenna is oriented in the along the direction of the electric field of the transmitting antenna. As the receiving antenna, okay? And this way is another antenna, the receiving antenna, right? The receiving antenna. As the receiving antenna is exposed to the E field of the transmitting antenna, an electric current is induced in the receiving antenna. Which is used to power the speakers of your radio, right? Or to paint a picture in the screen of your TV. Remember, we are talking about wireless, right, transmission, not cable TV, right? We're not talking about cable TV here. Cable TV just use a wire in there, but that should be like your cell phone too. It works like that too. Your cell phone has a receiving antenna there inside. And let me show you one possible transmitting and receiving antenna. It's almost time, right? Let's see, for our break, go. Transmitter, receiver, like I said, this thing is real life, okay? And we do have little toys that we can buy out there, like this one, see that? See this coil right in here? This coil is just like your magnetic dipole antenna, okay? This guy here, let's see, is both a transmitter and a receiving, okay, device. Let's see, this one, one must be the transmitting and the other the receiving, okay? That's what it is. And those antennas are connected to either one. Let's see if we have more here. We buy those things, it's not expensive, okay? But you have to know how to play with it, right? Right now, I'm working on a project that is using one of those devices. Let me show you my little toy. Okay, I'm going to stop sharing the screen so we can see it. Let's see here. How do I just on you go? Let's see. Okay. Yeah, I'm going to stop sharing my screen so you can see what we have right here in my hand. Is a little box that my electronic engineer did for me on my project. Okay, it's a receiving antenna, basically. That's what it is. Now I opened that for you so you can see on the inside. You see the coil? Let's see if I can get closer and closer. That's the coil, the magnetic dipole antenna that receives the electromagnetic waves of my sensor. There you go. This is my sensor right in here. I'm going to stop so you can see better now. So here you go. Here's my receiving device with my magnetic dipole antenna, one of those devices that you saw that I was showing to you, right, that you can buy. And here inside, I have a similar device, but instead of receiving, it transmits the data from my sensor. This is a sensor. This is a liquid level sensor. This guy works in a wireless fashion. You know, I open it, but the antenna is hidden here. You cannot see. Even if I open, you won't be able to see. But that's how those things work, okay? Two coils, one coil here inside, another coil here on this device that picks up the signal. The whatever, you know, and how do you encode your message, right? How do you encode? And that's another step. That's another step, how you encode your message. Right now, we're just talking about electric and magnetic fields, right? But right now, we're just talking about electric magnetic. But then, you know, note, I'm going to write it down here. Note that we can transmit and receive electric and magnetic fields with my antennas, right? The question here, how do you paint a picture in the screen of your TV, right? How do you transform those electric and magnetic fields into sound, right? There are circuits for that as well, okay? And that's another, you know, what you have to do, you have to encode the electric and magnetic fields. You encode them in such a way to reproduce the sound or the images that you have, okay? So that requires another circuit, another separate circuit, that same circuit that your book referred here. See that? To audio and video circuits amplifier, okay? So in radio and TV transmission, these electric and magnetic fields are encoded in such a way, to, you know, to command, right? The speaker of your radio, and the screen of your TV to reproduce a given sound and paint a given image. Okay? And that's another.
Sorry.
Yeah.
You are not sharing your screen, I think.
Yeah, thank you. Thanks for letting me know. So here you go. Note that we can transmit and receive electric and magnetic fields antennas, right? That's what I mentioned. So the receiving antenna is exposed, right? Is exposed to the electric field of the transmitting antenna. And electric current is induced in the receiving antenna, which is used to power the speakers of your radio or to paint a picture in the screen of your TV. The TV is nothing but just a radio and something else, right? If you know how to transmit sound to a radio, then you get that same circuit and implement that in your TV. But in order to implement that in the TV, you also have to know how to paint a picture in the screen of your TV. Okay, so note that we can transmit and receive electric and magnetic field with the antennas, with antennas, right? In radio and TV transmission, these electric and magnetic fields are encoded in such a way as to command the speaker of your radio and the screen of your TV to reproduce a given sound and paint a given image, respectively. Okay. But the basic idea of electromagnetic waves is this one I gave to you. Okay, in order to transmit a given sound, to reproduce a given sound or reproduce a given image, it's done by another circuit. Now it's 10 o'clock. Let's take a look here at our attendance, 1st of May. And by the way, I won't be able to announcement, okay? We will not have any class this coming Wednesday, okay? This coming Wednesday. So I'm canceling the class this coming Wednesday. And I'm gonna write that in the end. I'm gonna change here also. Okay, Wednesday class canceled, and I will have to readjust the schedule again, okay? It looks like we won't be able to cover some of this material here. Let's see, Einstein special relativity, then I'll try to cover as much as you can on electromagnetic wave, but don't forget, here is gonna be lab 8, right? Lab 8, 5, 6, let's see. Do lab 5 and 6 do. I should be able to correct them. Lab, here you go. Wait a minute, what's going on here? I need, lab 7 is here, okay. So lab 8 is gonna be transferred here. And it looks like we're gonna have only, I will, let's see, a fraction of light, particles and waves. Let's see, Einstein special. I will remember there will be no class, right? No class. I'm gonna put that here. I will adjust the schedule accordingly, and we'll meet again next Monday. Okay? So that's the announcement I want to make. There will be no class. There will be no class. There will be no class. It's coming. No class. It's coming Monday. It's coming Wednesday. That should be May 3rd. Okay. And let me take attendance here. Randy, are you there?
Yeah, I'm here.
Yeah, okay, thank you, Randy. Vanessa Bonilla, are you there, Vanessa? Thank you, Vanessa. Ashley Diaz. I don't see Ashley there. Natalie Espinosa. Thank you, Natalie. Janet Garcia. She just joined in, right? No, I don't see Janet here. Yeah, I don't see Janet. Okay. Are you there, Janet? No? Oh, yeah, Janet here. I'm gonna put a star. Okay, so Noor, are you there, Noor? I see Noor in my list, but I don't hear from her. I put a star here as well. Blanca Hernandez. Blanca, oh yeah, thank you, Blanca. Kelly Hernandez. Thank you, Joshua Jimenez. Okay, thank you, Noor. Now what about Joshua? Let's see, is Joshua here? I don't see Joshua here. Next is Alondra.
Present, Professor.
Thank you, Alondra. Kennedy, Lindsay.
I'm here.
Thank you. Daisy Mariscal. Let's see, I don't see Daisy here. Next is Yesenia Montes Rodriguez. Hi, Yesenia. Okay, I don't hear from Yesenia. I'm going to put a star here. Ryan. I see Ryan. Oh, yes, Janet. Okay, Janet, thank you. Janet Garcia. Yeah, right here. I don't hear. Ryan is here. Good. Artur Pacheco. Thank you, Artur. Leibelut. Thank you, Donia.
Here.
Thank you, Donia. Elika? Hi, Elika. Just let me know you're there. I'll put a star here. And Brianna Valencia. Did I skip anybody? Yeah. Here, okay, good. Where is Brianna Valencia? Okay, thank you, Brianna. And Justena Youssef. Thank you. We have a total of 15 to 6. Yeah, okay, good. So it's 10:06 right now. Let's go for our break.
Professor,
Yeah.
have you given any thought to the extra credit that you could give us yet?
Who is that?
Hi, this is Kennedy.
Yeah. Yeah, what's your question?
Sorry, you said that you were thinking about giving us extra credit, like you were thinking of an assignment or something to give us.
Yeah, let me think. I still haven't figured out which extra credit I want to give to you, but give me a few more days, okay? And
All right.
so let's see, 15, 10:07 right now. Break from 10:07 to 10:22 a.m. Okay, so see you in 15 minutes. Okay, I'm back here. Let's see, Yesenia is here, right? Yesenia Montes Rodriguez. And looks like someone else came in. Daisy, are you there? Yeah, okay. And Elika, are you there? Okay, now we have.
She was just texting me, but we were talking about homework, so.
Okay, so I'll give her attendance too. Good. So, okay. So, okay. Let's talk about extra credit, right? I just had an idea here. What could be a good project for you for extra credit? That it will require some, it will require some research on your part. Okay, and I'll help you out. I'm not gonna give you the straight answer, but I'll help you out somewhat on that. And okay, this extra credit involves no more than 10 points, okay? No more than 10 points for the extra credit. And it's due last day of class. Last day of class is going to be May 29 and it's due May 29, okay? And what we're going to do, you're going to do the following. Okay, extra credit, it will require some research on your part, and it is due on May 29. Okay, and the idea is the following. Let me explain exactly what it's all about. Okay, recall labs 2 and the other one is, lab 2 was electric field 2, right? 2, and there was the lab of the light bulb. Which one was that lab? Yeah, flashlight bulb. Lab 7. And lab 7. Lab 2. And lab 7, flashlight bulb. These were one lab, the only 2 labs that you had to fit an equation that was not a straight line, right? Was there any other lab that you have to do that? Just those 2, right? If you recall. In lab 2, you had to fit a power regression power equation, right? And a log equation to the data. In lab 7, you had to fit a third order polynomial. There's a little secret about that I didn't tell you. Okay? And the secret is the following. The equations that you got and the R square that you obtained are correct. The only thing that was not correct was the confidence level. But only for those 2 labs. And there's a reason for that. The confidence level table that I provided to you, okay? It's going to be kind of challenging, okay? But with a little bit of imagination, hopefully you're going to find out how to solve this problem. No more than 10 points, okay? It will require some research on your part, and it's due on May 29th. This extra credit involved lab 2 and 7. Recall lab 2 and 7. These were the only 2 labs that you had to fit an equation that was not a straight line, that was other than a linear fit. In lab 2, you had to fit a power equation and a log equation to the same data, right? In lab 7, you had to fit a third order polynomial to the data. The equation that you got and the R squared that you obtained are correct. You don't have to worry about that. The only thing that was not correct was the confidence level. And there's a reason for that. The confidence level table that I provided to you applies only to linear data, to linear sets, right? That's the little secret that I didn't tell you. However, despite of that, it is still possible to get the correct CL for the table, data, and equation, and regression equations. However, despite of that, it's still possible to get the correct, despite of that, it's still possible to get the correct CL using the table I provided, the table, and data that I provided you, and the regression equations that you obtained from the lab. Okay. So that's the story here that you gotta know. So based on that, I need you to figure out how to do that. Okay, how to do that. I want you to think about that. Don't lose any sleep because of that, okay? Because it's just extra credit, right? But there is a really nice, simple way of doing that. Okay, and as we go along, try to solve this problem. How to get, the correct CL using the given, using what was given to you, using what was given to you, okay? That is a way, okay? I'm gonna give you a hint. You have to plot another graph that ends up being a straight line, You have to plot another graph with the data that you have. That's a hint. The data that you have that ends up being a straight line. Okay, that's the hint I'm gonna give you so far. And I want you to think about that. Remember, you're not gonna have any class. We're not gonna meet again. We're not gonna meet on Wednesday, so you're gonna have additional time to think about that. I'm taking the Wednesday off because I have to do something, okay? So that's the story behind the extra credit, okay? Extra credit, let's go through that again.
How would
Okay.
you like the format for this? Would you like it how we put the Excel documents onto the Word document and just submit the Word document with the graph?
You're going to need the Excel document. You're going to need the Excel document. You don't need to use a Word document. Just, if you can solve everything in the Excel document, that's fine. I will correct that, okay? So along the way, I'll try to help you out, but I'm not going to give you the answer. Okay, I'm giving you this hint here. Okay, so let's refresh that. Let's review that. Extra credit, no more than 10 points. It will require some research on your part, and it's due on May 29. Extra credit refers to lab 2 and 3. This extra credit refers to the data of labs of lab 2, E-field 2, and lab 7, flashlight bulb. These were the only 2 labs that you had to fit an equation that was other than a linear fit. If you recall, lab 2, you had to fit a power equation, a log equation. Let's see, let's put this way. Yeah. Log equation to the same data. Lab 7, you have to fit a third order polynomial to the data. The equation that you got, the equations, the regression equations, right? The regression equations that you got are correct, right? And the R square is also correct. And we got R correct, and the R square you obtain are also correct. The only thing that was not correct, okay? The only thing that was not correct was the confidence level table. And there's a reason for that, the confidence level table. And there's a reason for that. The confidence level table that I provided you applies only to linear fits. Okay? That's the little, secret that I was withholding from you. Okay? So whatever CL you got for those regression equations, if you use the confidence level table that I provide to you without doing anything else, just straight whatever CL you got in there is not the correct one, okay? But I didn't subtract, I didn't punish you for that. Okay? However, despite of that, it's still possible to find, right? To find the correct CL using the table and data I provided you, and the regression equation, that using the table and data I provided you, and the regression equations you obtained from the lab. Based on that, I need you to figure out how to get the correct CL using what was given to you. Hint, you have to somehow plot another graph with the data that you have that ends up being a straight line. It is a procedure right, that will end up with a linear plot. It's a procedure, okay? Think about that, and we, along the way, I might give you a little bit more of help on that, okay? Let's put that here, extra credit, extra credit. Okay. Now we can move forward. There will be no class. It's coming Wednesday. So go back to the data that you got. Okay, it's gonna be individual. This extra credits and individual extra credits, right? Individual extra credit. You have to turn in a spreadsheet only. Okay. And now let's move forward, right? Let's see here. Okay, so we covered that. Okay, 24.1 is over. Okay, the electromagnetic spectrum is not difficult. right? It's not difficult to understand. So let's talk about the electromagnetic spectrum now. The electromagnetic spectrum. Okay. The electromagnetic waves that we generate with an electric circuit, right, have a frequency, and wavelengths, just like any wave, frequency, wavelength, and speed. Okay, frequency, wavelengths, amplitude, and speed, just like any mechanical wave, right? Just like any mechanical wave. Recall from physics 6, right? That wave has a frequency, wavelength, amplitude, and so on. Recall that mechanical waves have a frequency of oscillation dictated by the frequency. About the mechanism has a frequency dictated by the frequency of the source that is generating the wave. Okay? Example. If you have a wave in a string, right? Have a wave in a string that's being produced by an oscillator that oscillates at a frequency of 10 hertz, right? Then the wave that was generated also has this frequency. Okay. Okay, and the speed of this wave is going to be dependent on the medium that the wave travels. Okay? The amplitude of the wave is going to be dependent also of the amplitude of the oscillation. It's going to be dependent, but it's not going to be the same. It's going to be dependent, but not necessarily the same, right? But not necessarily the same. Okay, if you have a wave in a string that's being produced by an oscillator, then one, the wave that is generated also will have this frequency. Okay. Two, the speed of this wave is going to be dependent on the medium, right, that the wave travels. Just like the wave in a string. The wave in the string depends on the mass, the linear mass density of the string, right? If you remember that, plus the tension in the string. The amplitude is going to be dependent, but not necessarily equal. Not necessarily equal to, it's going to be dependent on the amplitude of the wave, but not necessarily equal to the amplitude of the oscillator. Here you go. And 4, the wavelengths will obey that relation that we saw, right? We saw in physics 6. Right? And what was the relation? It's not difficult to memorize because it's very similar to the equation for the velocity, right? So what's that? The speed of a given wave is going to be given by the wavelengths divided by the period of the wave. But recall that 1 divided by the period is also another way of writing the frequency of the wave. So once you know the period and the frequency of the wave, you can know what you will know what's going to be the wavelengths. That's just a refresher, right? What we saw in physics 6. Like that. Okay, so how do you translate that this information of the mechanical wave into an electromagnetic wave? That's the question I'm going to ask you. Okay, so how do you transfer this information from a mechanical wave to an electromagnetic wave? Okay. Okay, first, the relation, V equal to lambda T or V equal to lambda F, right? Let's put here. First, the relation is a genetic relation that applies to any wave, whether it's a mechanical, whether it's a sound wave, whether it's an electromagnetic wave. Okay. Whereas that other relation that you saw, remember that other relation that you saw for a mechanical wave, for a compare that to the speed of a wave in a string. Okay, speed of wave in a string. Do you remember that? Let's see here. Hopefully I'm right here. I'll check. Here you go. Is going to be given by what? The tension. Oh, no, I'm going to put F divided by mu, right? Oh, no, it's not what it is. Let's make sure that's the right one. I'm quite sure it's correct. Is speed of a wave in a string, right? Stretched string. Now they put mass of the string. Let's see. Wave speed on the string. Okay, they derived that here. I want to see the final answer. Yeah, that's right. F is the tension. Mu is the linear mass density of the string. The string is assumed to be homogeneous. Same diameter, okay? Same mass along the lengths, in the same lengths. That's what this thing is all about. mass of the string divided by the length of the string. Okay, compare that to the wave of or the speed of wave of the string. This equation applies only to a wave propagating in a string. It's not a generic equation. Propagating in a string only. And we have other equations for other types of waves. Okay. In the case of an electromagnetic wave, already mentioned that here in class, wave, comma, the speed of the wave, is given by the dielectric constant, is a function, right? Is a function. I'm not going to prove that. Is a function. We cannot prove that here. Of the dielectric constant and the permeability of the dielectric and the permeability constants. What those are? They are the epsilon naught and mu naught. Okay. And I'm going to symbol. We cannot, like I said, we cannot prove that. All I can say is to point you out to that pair of equations that I showed to you, okay? All I can do is to point you out to this pair of equations that I showed to you. We have this epsilon naught and mu naught right in here. And by the way, when we are talking about free space, okay, like here in this region of space, where we have no current flowing whatsoever, where we have no electric charges whatsoever, this set of the equations reduces to something like that, okay? And now we have some sort of symmetry between those two, right? Okay, and what you end up having here is related to the speed of the wave, okay? For the case, in the case of, not in the case of an electromagnetic wave, for the case of an electromagnetic wave, the speed of the wave is the dielectric and permeability constant, epsilon naught and mu naught, okay? And it's given by something like that. 1 mu naught epsilon naught okay? If you do the math, you're going to get very close to 300,000 kilometers per second. Let's do that together. You know, that was the discovery that Maxwell made, okay? When Maxwell was cranking up his equations, he got that as the speed of the wave. And then when he plugged in the numbers in there, at that time he already knew what was the value of epsilon naught and mu naught. You know, he got the 300,000 kilometers per second that almost everybody knows, right? So let's do the math just to be sure about that. Dielectric constant, right? And don't forget those are the constants for the vacuum, right? Dielectric constant and what's the dielectric? No, let's see. Dielectric constant. Let's see. Well, some books call it this epsilon naught, the dielectric permittivity. Okay, it's called permittivity, not dielectric constant. Permittivity of free space. The permittivity, and the permeability constants of free space. By free space, we mean of free space. By free space, we mean vacuum. The vacuum. which by the way is very close to the value of air. Okay, so permittivity. Let's see if they have the permittivity value here. Blah, 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 blah. No. Permittivity of free space. That's the value. Okay. Let's write it down. Even better, I'm going to use my favorite software to do this math for me. So you can see everything step by step, right? And I'm not going to neglect the units. I'm going to go for the actual units, okay? So here you go, 1 divided by square root of epsilon naught. Oh, wrong one. Epsilon naught times mu naught. And now we have to write down what are the numerical values of those parameters. Don't forget, I am writing epsilon naught because it refers to the permittivity of vacuum, which is very close to the permittivity of air as well. The permittivity of vacuum is written in your book, is written on the internet. You can look at that, and I'm going to put everything here. 8.85, okay, I don't need to go for more than that, times 10 to minus 12. And then we have to worry about the units. Second to the fourth power, ampere to the second power, and then we have to divide that by cubic meter and kilogram, okay? Cubic meter and kilogram. That's the dielectric. That's you know, he called the electric constant, but that's another name, permittivity. And the other permeability. The other is the permeability of free space. And again, free space means vacuum. Let's write it down. Gotta define everything here before we can move forward. Here you go, but then instead of epsilon naught, I'm gonna put mu naught, and the number is different too. 1.26, so I'll put 10 to minus 6, and the units are different. The units are different. Meter times kilogram divided by second square, right? Ampere square. And in the process, we're going to do, no, we're going to replace here epsilon naught, replace here for mu naught, and we're going to crank up all those numbers. Do you see what happened? The ampere square second to the fourth power cancel out with the ampere square second to the second power, right? And it also cancel out with the kilograms. Some of the meter also gets canceled out. And look what happens. We end up with the meter per second square. I'm sorry, we end up with the second square per meter square. That when you invert it, you get the unit of speed, right? Let's go further. Let's go further. Expand. Okay, and we get 3.33 here. And I want to get this guy outside the square root. Let's see how we're gonna do. Let's see, compute, I'm going to factor it. Yeah, hopefully I can get it now. Nope. Strange, right? He put this value here. Simplify. Why did he put 512? There's something wrong here. Huh. Yeah, it's a little bit puzzling why he put 512 here. But let's see. Let's finish this calculation here. Let's see if we get the right value. Yeah, we do get the right value. 299,000 kilometers per second. Okay, that's the little secret. So all those quantities that have this complicated unit end up, whenever they're combined, ends up being the meters per second speed. Okay, but now that we found the speed of the light, I'm gonna put like 300,000 kilometers per second. 1, 2, 3. I'm gonna put a comma here. 1, 2, 3 kilometers per second. Okay. Don't forget that what you see right here must also be equal to that genetic equation that you saw for the speed of a wave. Okay, and I'm gonna specifically put here genetic. Okay, and then this one I'm gonna call particular, right? I'm gonna call that particular for the let's see, string. I'm gonna put string. Okay, electromagnetic wave. Here I'm gonna put electromagnetic wave. E&M. Okay. Now the question is, what's going to be the frequency of your wave? Okay. We call that the already mentioned before, right? The frequency of the wave is dictated by the frequency of the oscillator that is generating the wave. And the question, which oscillator is that? Okay? The question, which oscillator is this one? Is that? Well, the question is simpler. It's simple. Remember that in order to generate an E&M wave, electromagnetic wave, you need an AC circuit. Okay, that's what you need. It's going to be that guy that's going to produce the current that bounces back and forth. Okay, and the frequency of your AC circuit, is going to be the frequency of your E&M wave. That's what the oscillator is all about. That's what the oscillator of your electromagnetic wave is all about. To generate an electromagnetic wave, you need an AC circuit. And the frequency of our AC circuit is going to be the frequency of electromagnetic wave. Okay? In the case of the power line at home, this frequency is around 60 hertz. 60 hertz. Consequently, if we plug an antenna to the wall, to your wall, at home, that antenna will generate a wave, a sinusoidal sinusoidal wave of 60 hertz. Okay? So now the question that you have to ask yourself, what is going to be the wavelengths of this wave, okay? Just plug in 60 hertz into this equation and find the wavelengths, okay? Simple enough, right? So, there you go, that's you go. Don't forget that V equal to F times lambda. Oh, wrong one. This one, here you go. Substitute here. Don't forget that lambda, not lambda, frequency is going to be 6 hertz, 60 hertz only, which by the way is hertz is 1 divided by seconds, right? Substitute it here and we end up with a wavelength that long. It's 4 million. I'm almost 5 million. 5 million meters. Okay. Going to be what's going to be the wavelength of this wave. Okay. If you do the math, you get, lambda equal to 5 megameter, okay? Megameter, or 5 billion meters. But that's not the only, but this is not the only frequency, electromagnetic frequency that we can get. There are several others. There are several others. Okay? So much that we have, so much that we have what we call the electromagnetic spectrum. Okay. This type of wave that you see here is kind of in the range of what we call the radio waves. And even we call that radio waves. Okay. Here's the electromagnetic spectrum. Here is 10,000 meters. This is one here. Yeah, 10,000 meters. Okay. 5 million meters, a little bit to the right, to the left. So should be, low frequency is a low frequency radio wave. Okay. The radio station that we usually listen to, they are, the music, the sound that we hear are transported by electromagnetic waves. Electromagnetic waves that are encoded in this range of frequency. Okay, 10 to the 4, 5, 6, 7, 8, right? AM waves is 10 to the 6 hertz. 10 to the 6 hertz is a megahertz, 1 megahertz. Okay, which correspond to a little bit more than 1,000 meters of wavelengths. And then the FM wave are generated by circuits that have a frequency of 100 megahertz. Have you heard that? 100 megahertz. That's what the coffee radio station is all about. It's about the frequency of the circuit that they use to generate that wave. The AC circuit and microwave, in the case of your microwave oven, extends throughout this range here. They are all considered radio waves. Microwaves, FM, AM. Here's the range is anywhere between 10 to the 9s to 10 to 11s. 10 to the 9 is 1 gigahertz. 10 to 11 is 10 gigahertz. Your microwave oven has an electric circuit or an electronic circuit that oscillates at this frequency very fast. And think about that, how fast it is, okay? Human beings cannot reproduce this type of circuit, this type of oscillation without resorting to electrical circuits. My hand, the fastest that I can go is my hand is 5 hertz. 5 hertz, which is the natural frequency of the human body. That's the fastest I can go. So it should be, there's no way I could produce a wave of this frequency here in the gigahertz region. As we move towards higher frequencies and lower wavelengths and shorter wavelengths, okay, we get into the region of infrared waves. The infrared wave was discovered back in the 1700s. Okay, let's take a look at the history of infrared waves. Infrared waves. Okay, discovery of infrared waves. 1800s. In 1800, William Herschel, okay, conducted an experiment measuring the difference in the temperatures between the colors in the visible spectrum. Okay, so at that time they already knew that a glass prism could decompose the white light into several colors. And this guy started wondering, what if there are other colors that I cannot see with my naked eye, right? That's what this guy was wondering. William Herschel, he also discovered the planet, right? So what did he do? He gets a thermometer, okay, and start measuring the temperature of each of those colors, okay, in the visible spectrum. The results showed an increase in temperature from blue to red, and then he moved his thermometer outside the red, and then he discovered that that region next to the red also had a temperature, okay, also had a temperature. And that's how he discovered this invisible light that today we call infrared. And the puzzle of infrared, see, American scientists, okay, most encyclopedias and physics book credit the great British astronomer William Herschel, who discovered infrared radiation in 1800. Wikipedia must have a nice article too, you see. Infrared, sometimes called infrared light, is electromagnetic radiation, right? You go. Definition, relationships, natural infrared regions. Let's see, visible limit. Let's see if they talk about William Herschel here. Herschel. In 1800, the astronomer Sir William Herschel, German-born British astronomer and composer. He was also a composer. Okay, collaborated with his sister. Okay, and discovered that infrared radiation is a type of invisible radiation in the spectrum, lower in energy than red light by means of its effect on a thermometer. Okay, slightly more than half the energy from the sun was eventually found to arrive on Earth in the form of infrared. Okay, so that what let's see, where's my book? Not here, this one. Yeah, this one right here. Okay. Okay, so that's the region of the electromagnetic spectrum called the infrared. And then we have this very small window through which we poor human beings can visualize with our eyes. Okay. Think about that, you know. We would never want to go blind, right? And yet, it is our eyes, and yet our eyes can detect only a very small window in the electromagnetic spectrum. The colors red, orange, yellow, green, blue, all the way down to the violet. The very small window, here's the frequency. Frequency is on the order, here you go. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, between 10 to 14 and 10 to 15 hertz. That's how fast a circuit we must create to generate visible light. 10 to 14, between 10 to 14 to 10 to 15. The wavelength is going to be in the range of nanometers, not nanometers, it's going to be micrometers, fraction of a micrometer. 10 to minus 4, 10 to minus 5, 10 to minus 6. 10 to minus 6 is 1 micrometer. 10 to minus 7, 10 to minus 8, 10 to minus 9. We usually say, you know, the frequency, this is the much frequency, right? 10, let's see, 1,000, 10 to the third, a million, 10 to the 6, a billion, 10 to the 9, a trillion, 10 to the 12. Okay? It's 400 trillion hertz. It's gonna be, you know, kilo, mega, giga. The next one is terahertz. And that's the frequency of the wave in the visible spectrum, 4 to 7.9 terahertz. Okay, and then what would be the wavelengths? Wavelengths is it's not difficult to memorize. It's anywhere between 400 here to 600 nanometers. Nanometers is 10 to minus 9. Okay, so you gotta remember that. And then what we have past the visible frequency of the spectrum, we need our break very soon, right? We have the ultraviolet. The further away to the right we go in this spectrum, the more energetic the electromagnetic wave becomes. Ultraviolet, this is, you don't have to memorize those frequencies, but you have to memorize the order, right? Radio waves, infrared, visible, ultraviolet, X-ray, and gamma rays. You have to memorize the order. You have to know that gamma rays is the most energetic type of electromagnetic wave, X-ray is the second most energetic, and so on, okay? So much that we call those two types of wave ionizing radiation. Radiation that ionize atoms. It's not good for you to be exposed to ionizing radiation. Okay, that's the electromagnetic spectrum, okay? And what else do we have here? Wavelengths of visible light. Pulse oximetry, okay, that's a type of device that uses electromagnetic wave to measure the oxygen in your blood, oxygen saturation in your blood. It was very important during the COVID pandemic. That device was very important. Okay, LEDs can be used to determine the oxygenation in your blood. It's a very cheap device. At the beginning of the pandemic, they didn't know that all they had to do was to measure the oxygen concentration in the blood of a person. They didn't know that. It was a very simple measurement that you need to do it to prevent the death of someone else. Later on, they discover, oh my goodness, so many people died because of that, right? That's and that's done with an electromagnetic wave. Here you go. Fingertip pulse oximeter. See? A cell of fingertip pulse oximeters that are designed for at-home use, like the ones shown here, soared during the COVID-19 pandemic in 2020. Okay? But before then, they didn't know that. One of the more dangerous symptoms of COVID-19 is respiratory pneumonia. People were getting with a low oxygen in the blood, and that leads to hypoxia. And whenever you become hypoxed, whenever you have a hypoxia, You become very excited, very happy, okay? But the less and less oxygen you have in your blood, the more dangerous it becomes. So people would see that the loved one becomes happier and happier. Oh, he's doing very well, right? No, he's not doing very well. He's about to die if you don't do anything, okay? Which attacks the person's lungs and inhibit blood oxygenation process. Careful monitoring of a person's blood oxygen saturation is critical in determining the level of care that's needed. Okay, so that's done with electromagnetic waves in the infrared region of the spectrum. By the way, let's see. They say here, yeah, that's the frequency. Let's make sure referring the light, in the visible red part of the visible. Well, it's not the infrared, it's the visible. It's the, yeah, between the infrared and the red part of the spectrum, okay? That's the light of frequency F1 can be seen with the naked eye, okay? So let's document that. What time is that? 11:20, right? You can get, there are several others. So electromagnetic spectrum. Electromagnetic spectrum. Order of low to high frequency, right? Long to shorter wavelengths. What's that? Radio waves, infrared, visible, ultraviolet, oh gosh, what a shame. Ultraviolet, what else? X-rays and gamma rays. Those are within the radio waves. We have some other, types of radio waves that we call what? Let's go back to the book. We have VHS, UHF as well, okay? And then we have AM. He doesn't show UHF here, okay? AM, FM, and microwave. AM, FM, amplitude, modulated amplitude, the first one. The other one is the frequency that's modulated. The other one is microwave. Okay, let's see where the UHF fits into this spectrum. You also have ultra high frequency. That's what UHF stands for. Okay, ultra high frequency. Ultra high frequency encyclopedia. Oh no, that's in Portuguese. You don't want Portuguese. UHF, Wikipedia. Well, let's go anywhere. I'll try to put English here. Let's see. Yeah. Radio frequencies in the range of 300 megahertz to 3 gigahertz. Let's see where it fits in the 300 to 300 mega to 3 giga. Okay. 300. Yeah, 300 megahertz. 300 megahertz is somewhere 4 or 5, yeah, within the AM to 3 giga, right? So it overlaps the AM, FM, and microwaves region. Okay, ultra high frequency. Then you have UHF. We have, let's see, I believe we have LHF as well. Let's see, not this one. Ultra high frequency. Let's see, propagation characteristics, applications. United States, the different ranges of UHF. I think it's low HF, high, no. Oh, there's another one I don't remember now. Ultra high frequency. Okay, super high frequency. Okay. Radio waves with frequency above UHF band fall into the super high frequency, SHF. And then we have VHF as well. Very high frequency. Okay. Let's take a look here. Unfortunately, they don't have the electromagnetic spectrum. Oh, here you go. By country. Each country has their own laws. They have to reserve the part of the spectrum, some part of the spectrum, so there is not interference, okay? Television systems, see that? Japan, the Americas, French, Ireland. There is a international agreement that dictates where you can operate in the electromagnetic frequency of the spectrum. VHF, very high frequency, okay? And but the most important are those ones that I mentioned to you, the radio waves, you know, infrared, visible, but okay, visible wavelengths are in the range of 400 nanometers to 600 nanometers, a little bit more than that. Okay. I believe 660, something like that. Red color is in 660 and 1126. What else can I tell you? So that's what we have for the electromagnetic spectrum. Okay. In free space, don't forget, it's 300,000 kilometers per second. Speed of the light, I covered the speed of the light. Where it comes from? It comes from the permittivity constant and permeability constant. Here you go. Here's the equation that I spelled out for you. The same calculation that I did, the book did as well. And then we have energy carried by electromagnetic waves, okay? Those electromagnetic waves has an energy, and we are going to talk about that. And by the way, we have already covered that. You're going to see why we have already covered that, okay? Once we come back from the break. So 2-4, then we have, I'm going to skip the Doppler effect, and we'll be able to finish this chapter today. Okay, so here you go. Break between 11:28 and let's see, 11:43. Yeah, a.m. Yeah, that's right. And I see you. Do you have any questions?
Professor, Alika typed in the here in the chat.
You're breaking. You're breaking up. Can you type for me there in the chat box?
Yes.
Okay. Okay, so I'm gonna pause my. Okay, I'm back here and. Okay, energy carried by the electromagnetic waves, right? Let's take a look at that. Carried by electromagnetic waves, Okay, note that electromagnetic wave is made up of electric and magnetic fields. that move in space as a wave, okay? Also, recall that the capacitor and the inductor have an energy density, right? Energy density given by, right? What do you remember that? The energy density of the capacitor and the inductor. Okay. So for the case of the capacitor, we had an equation just like that. Half epsilon, epsilon naught, epsilon, no, epsilon. Hey man, why I cannot get that? Let's see, alpha, let's see. Alpha, okay, good. Why cannot get the epsilon? Epsilon. Like that? No, maybe it's that. Okay. With n at the end, half of epsilon naught. It's not the, remember, it's not the dielectric constant. This is the permeability constant of vacuum. And then we had this other parameter here. This states that the energy is not stored in the charges of the capacitor. It's not stored in the conductor of the capacitor. It's actually stored in the vacuum of the capacitor, in the vacuum where the electric field lies. Okay? The energy is stored in the electric field, and the electric field can move through vacuum. In the case of the inductor, we do not have any, we have something that's very similar to. It's not much different. If one goes with the square of the electric field, the other goes with the square of the magnetic field. If one depends on this electric constant, right? On the permittivity constant, the other is going to depend on the permeability constant of vacuum. That's what we got for the capacitor and for the inductor. Now, as before, we learned that the energy is stored in the magnetic field here. Because an electromagnetic wave has both electric and magnetic field, okay? Because an electromagnetic wave has both an electric and magnetic fields, okay? The energy of the wave is carried along these fields. And that's what your book has. Okay, so here you go. Let's take a look. Okay, that's the equation. Magnetic energy per volume. Consequently, the total energy in electromagnetic wave in the vacuum, okay, not in other media, is going to be the sum of those two fields. Let's write it down. These two fields, comma, the net energy of this wave, and the net energy per unit of volume, right? Per unit of volume of this wave is going to be the summation of this, the sum of these two separate components, or U equal to UE plus UB. UE is this term. UB is this term. Let's see if we can do anything else. Okay, the first obvious thing that we can do is to factor, right, the half of both terms. So that disappear. Okay. Okay, that's the total energy. In an electromagnetic wave propagating through vacuum or air, the electric field and the magnetic field carry equal amounts of energy per unit volume, okay? So he didn't prove that. It's possible to prove that, but he didn't, okay? So this term here is going to be equal to this term right here. It's possible to here write this equation, right, for the total energy, okay? But for an electromagnetic wave, we have the following. Like I said, it's possible to prove that, but you don't do that because it requires a higher level of mass. Okay. We have the following. So the net energy per unit of volume can be written either in terms of the density of electric energy or the density of magnetic energy. Can you remember that? Okay, some things we have no choice. We have to memorize, okay? But they're not difficult. Certain things are not difficult to memorize. Either one. So the amount of energy carried by the electric field is the same amount carried by the magnetic field. That in the part that applies for an electromagnetic wave. Okay, and there is a relationship between those two fields. Okay, in an electromagnetic wave. If one is equal to the other, let's do that. Let's look at the consequences of that, right? If this guy is equal to this guy, what does it mean? What's the relation between the electric and magnetic field, okay? So if what? Half cancels out. And now we can come up with a relationship that you saw before. There you go, like that. And let's not forget that what you see here can also be written as the velocity of the light. C, right? What you have here is the velocity of the light square. And if the velocity of the light square is equal to that, it means that the electric field is going to be C times B. Let's see if it missed anything. Yeah. Okay, so the electric and magnetic field fluctuate sinusoidally in time, right? And there is this relationship. Oh, there's more that we can do. There's more that we can do. Okay, both the electric and magnetic fields very sinusoidally in time. So they're both sinusoidally. Let's see, sinusoidally. Oh, in time. Sinusoidally in time. So what you have here is in reality a function of time. Why do they vary sinusoidally in time? They vary sinusoidally in time if, right, if the source of the electric and magnetic field is an AC current, right? If the current, you know, or you know, or if, you know, the current I is equal to I naught, right? Maximum current times sine, okay, 2 pi ft. Here's the term of the frequency, right? This implies that both E and B will vary according to the current, or okay, like that. Go. E is equal to B CB, okay, and then I'm gonna put here amplitude E naught that we do not know yet, but we can find that out. Okay, let's not forget that. Here you go. I'm gonna put this way. Here you go. I'm gonna put this way. Let's not forget that the magnetic field can also be here written as something like that. Do you see here the frequency of the electromagnetic current, of the electromagnetic wave? That's what this F is all about. Can be the frequency of the light, can be the frequency of UV light, can be the frequency of infrared, the frequency of your radio wave, and so on. Okay? And now what the book did, we have seen that before, right? We can define now the root mean square value of those respective fields. So here you go. The RMS is going to be given by E naught divided by a square root of 2. I'm gonna put a half here. Oops. Square root of 2. This is the square root of 2. Okay, and we have the same thing for the magnetic field. So funny, right? To put this 2 here as a half there. Let me put the actual. We're running out of time soon. So I gotta put the square root here. Good. Now, okay, and now we're gonna have B, right? B naught square root of 2. And what else can I do here? We can have the C there, right? The E is going to be, let's see, B naught is going to be E naught over C, or E naught over C, right? Square root of 2. That's what we have here. Okay, and we're running out of time right now. And now that you know that, right, that the electromagnetic wave carries energy with it, now you can start thinking how you can tap into the energy of an electromagnetic wave to do some useful work, okay? How you can tap into this energy to make some useful work. One way of doing that is just to look at plants, right? Plants are just nothing but the solar, organic solar panel. It takes advantage of energy of the electromagnetic wave to convert that into something else that will make the plant grow. And then nowadays we do have a semiconductor device called solar panels that can convert electromagnetic wave into electricity, okay? And that's 12 noon right now. We can stop, and next time we'll pick up on this and finish the chapter, okay? Any questions? Okay, we are going to skip this chapter and then go into polarization. Okay, so see you next Monday, and make sure you start thinking about that little extra credit problem that I assigned to you.
Professor,
Yeah,
will the document of the notes be uploaded today?
yeah, I'll do that right now.
Awesome. Thank you so much.
All right.